Hi, welcome to the video. In this session, we're going to talk about networks graphs in data visualization. So, networks are very flexible to represent different problems and different situations in real life. So, in this presentation, we will go over in how to create networks in transportation and logistics problems, in social network analysis, and also for databases. Now, what are the benefits of using networks? First, is that they can capture complexity. You can see the relationships inside a system. So it's really important because you can also find which nodes are important in the network. You can analyze the topology, the shape, right, the configuration that the system has. So when you want to create a network, you will need nodes, which are entities. Typically, they will represent people if we're talking about like social network analysis. But if we're talking about logistics, like supply chain management, nodes will be the customers and also like warehouse or deposits. And the links or the edges in our network will be the roads or the connections, right? If between between two nodes or more nodes. Okay, so mathematically speaking, we use this notation G equal, we have V and E, where V is the set of nodes and E is the set of edges. So if you want to create a graph network, you will need to define this, the nodes and the edges, the connections from what is the origin and what is the destination. It's important to mention that the nodes can have some different like properties. If we're talking about a warehouse, they might have capacity, for example, or if the node's a customer, the information can be the demand, right? Yeah, what is expected that that customer is going to order. Same thing with the links, the edges. We can add weights. Typically, if we're talking about logistics, that will be the cost to transport one unit from one link to one node to the other, or we can also have distances as weights. Okay, so let's discuss three different applications: transportation logistics, social network analysis, and graph databases. They are big. The three of them are really big. For example, in network logistics and optimization, let me tell you that transportation companies, airlines, they use on a daily basis networks. They analyze their networks and make decisions based on their network diagrams. So this is the most basic example, a very basic problem and well known in optimization, which is called the traveling salesman problem, TSP. In the TSP problem, there is a salesman, and the idea is that the salesman is going to requires to visit multiple customers. It can be, let's say, 10 customers or 20 customers. They can be located in different cities or even inside within the same city. So the idea for the salesman is to find the optimal route, so which is the sequence of the visits in such a way that we want to minimize the distance or the time. So, or initially it looks like a simple problem. So let's say that we have here some nodes. Like let's I'm gonna focus only in this part of the diagram. So we have here one, two, three, four, five, six nodes. So in how many different ways or how many different sequences we can visit these locations. So initially there are six options. So the salesman can go to any of the six, right? And once the salesman visits that first node, then there are five remaining, right? And then four, three, two, one. Therefore, the number of options, if there are only six customers, is 6 factorial, which is not that big, but if you consider that only six customers, it's a small amount. Now in real life, think about big companies like Amazon, Walmart. So the number of customers is going to increase, right? Therefore, the complexity is it's way higher than this. So if you have 1,000 of customers, then it's a complex problem. Here, it is really important to start learning some optimization tools. They are not included in this course, but let me tell you that optimization is really important in real life, and it can be connected with analytics, with data science. Let me show you a real quick where they're connected. I have here this one, this slide. It's just a reminder, and then I will go back to the model. So remember that in analytics, we have four different study types, right? We have descriptive analytics, what happened in the past. Diagnostic analytics, this is like EDA, basically. So these two, it's about the past, the descriptive and the EDA. And then the one that most people like is predictive analytics, what will happen. But companies, of course, they want to predict what's going to happen, right? To make a forecast, make a prediction. However, it's there is a need for prescriptive analytics, and that's like how can we make it happen, and what should we do in that scenario? So what is my best solution under the predictions, under the circumstances that you are predicting? So in prescriptive analytics, you have a mix here between some data science models and also optimization. Because with optimization, you will find the best possible solution. So for this specific example, this is the mathematical formulation to optimize and get an optimal solution. So typically in optimization problem, there will be an objective function. It's something that you want to minimize or maximize. In this case, we want to minimize the total distance to visit, like the different cities or customers. You have parameters and variables. So here the parameter will be Cij. That's the cost or the distance from going from one specific node I, to a node J, from node I to node J. And Xij, that will be our decision variables. So there will be 1 if we use that path, or 0 if we don't use that link. So we want to minimize the total distance in the final route. And of course, it's subject to some constraints. So just to give you an idea of these constraints, I don't want you to be experts in optimization, but the first constraint means that from one node or from one customer or one city, you're going just to one more, just one. It's like you cannot go to multiple at the same time. That's why you have the equal to one. And same idea, you can arrive to one node only from one. That's the constraint here. And then, of course, there is another constraint to avoid subtours in the final solution. So let me tell you again, and I want to emphasize this. Networks are really useful for many companies, especially for transportation solutions. When they want to design their supply chain, they use network analysis and they use optimization to find the best possible solution for them. This is a more general problem also in optimization. So you have one depot or multiple depots. I want to visit your customers, and you might have one or multiple trucks, right? So you need to find different routes. Now, this in real life, the problem is more challenging because there are in some cases another constraints such as the time windows. Time windows mean like, okay, you can bring the product, but only in this time window. There are some restrictions. So that happens, especially with like big supermarkets. They will ask their suppliers, okay, you can deliver your product only in the morning, for example. So that adds more complexity to the optimization. All right, so let's check the second application in social network analysis. This one is big too. So companies use this to analyze like how's the relationship among different departments inside the company. They can see like, okay, which individuals of which areas are interacting. They can analyze the workflow, right, between the areas, and even they can identify collaboration opportunities, or like in which connections they need to like pay more attention, invest in more resources to enhance like the information sharing and the productivity for the company. Now in social networks, if you go to, like social media, it's really important this analysis to find influencers, like important people, to analyze how a fake news is gonna spread, or how in general a news is gonna spread. Even this social network analysis is helpful to see how a disease is gonna spread in real life, to analyze that part. So this is a really nice way to represent social systems. And also, there is a lot of theory. There are courses about this. You will find a lot of libraries, first to visualize and also to compute some metrics in that network. We will come back to this example once we're working in Colab later in the video, and I will show you how to start creating these social networks. And the third application is for graph databases. I'm sure that most of you, especially if you're working or if your background is in like computer science or related, I'm sure that you have seen a relational databases, SQL. So in relational databases, it's the standard in most companies, especially for transactional databases. You will find a relational database. So we have tables, right, with information, and they have some relationships, some keys, they are connected. And if you want to explore the data, you need to perform, some queries, joins, select, where from, those are the typical commands in order to access to the required information. So this is one way to represent the data. And so it's really good for transactions. However, when you have big data or more complex relationships, maybe you are missing something. You cannot visualize that unless you perform a query. So with graph databases, we can see all the relationships right away. So it's not, instead of having tables here in a graph database, the idea is that we have nodes. We can see the connections, so we can spot if there are some patterns or relationships in our data. So they are flexible, and we can understand better our data compared to a relational database. So let's see how to create a graph database. This is just a quick example. I will ask you to go to Neo4j. Neo4j. So this is just one alternative to do this. Please create an account. You can use your Google account. Okay, while you're doing this, you will be asked your information, email, and all the stuff. Even it will ask you for your name, organization, and just start creating a network graph. It's just a way to show you like how they work, and it's nice what they do when you're adding your name, your information. They start creating the notes and the links right away. Okay, so once you do that, please, it will take time the first time because you will need to create an instance. But I want you to go to here, learn. So if you need to pause the video for if you are, like creating the instance, you can pause it. But go to learn, and once you are here in learn, there are some sample data sets. There are 4 sample data sets, and they have, like code with questions to guide you in how to use the language to create the graphs here. So the name of the language is Cypher. Cypher. Okay, so please go to movies. So when you open this is where maybe when you create a new instance, it will take time, this part. But once you're ready, in this data set, pretty much first we're going to create like we were going to load all the information. So the information here is just there are movies. So you provide the name of the movie, the title, right? And some information, some attributes. And also we provide information of the actors that are performing in that movie. So this is how we create the relationship. We create the entities and we also connect them. These are the relationships acted in or directed the movie. So we have the name, the link, and again the relationship with the other entities. So we have people, we have movies, and we have different connections here, different links. So to load this information in this chunk of code, there is here the execute. You see here the symbol execute. Just click. So it will create here a panel on your right where it's gonna run all the information that you're providing. So it's loading, like the movies and the different actors. Okay, and then uh, let's say that you wanna check for a specific actor. Here we have Tom Hanks. You wanna see, okay, in which movies uh, Tom Hanks, like what was involved in which movies, and you wanna see the path. You wanna see a network for that. So let's run the second chunk of code, and it's gonna create a network. If you cannot see it, like the names, so please click here to expand it. So once you expand the frame, and if you zoom in a little bit, you will see in the database, you see that the actor Tom Hanks, it has like different relationships with the movies. So these are the movies in which Tom Hanks acted in our database, and you also have the directors of the movies. So it's a nice way to visualize your data instead of tables. This is like a flexible way to start visualizing your data. Very interesting. I encourage you guys to please go over the rest of the tutorial. There are more steps, so you can see different codes. There are more specific questions to find. Let me show you just one here. I think it's step number 5, I believe. Number 5, this one. So 6 degrees of Kevin Bacon is like, for example, I want to find like the closest path between two actors that maybe they have not acted together, but I want to find the the path. Like, okay, so how can they can be connected? So let's find the shortest path. That's an optimization algorithm here to find the shortest path between two actors, Kevin Bacon and Meg Ryan. So this is the shortest path between these two actors. So Kevin Bacon acted in this movie. The name is A Few Good Men. So Tom Cruise also was part of the same movie. And then we have the Tom Cruise acting in Top Gun, the first one, and there is Meg Ryan here. So this is the shortest path between these two, between Kevin Bacon and Meg Ryan. Again, using these data structures, these databases, graph databases, you can answer different questions and visualize the relationships in a different way than traditional databases with just tables. So it's a different approach. Okay, so before we go to Colab, just a quick network classification. There are different classifications. This is not like a standard or the unique way to classify them. This is just some ways to differentiate the networks. So some of them are directed network graphs, others are undirected. Directed means that the edges, the links, they have a direction. For example, Twitter followers. So you follow someone. But in other cases, it's undirected. For example, in Facebook, if you're a friend, it's like both ways. It's not like you follow someone, no, you're a friend. There is no direction. It's whether it's just there is a link or not. In some cases, we will have weighted or unweighted networks. This means that the links, they have, like a property. For example, if we talk about the distance or the cost to connect to nodes, then it's weighted. Network can be also be static and dynamic. So in real life, most of them are dynamic, to be honest. There are some circumstances where they can remain for a period of time static, but static means that the structure remains unchanged over time, while dynamic means that it's changing, it's evolving, right? Like in social networks, you add new friends, so maybe your network is expanding at some point in life, and another point in life is gonna be like getting smaller. You don't know. All right, so let's go to the notebook to learn how to visualize networks, how to create them. Okay, so this is the first problem, and the library that we're going to use here is Network X. It's simple to use, so you can visualize networks, and also it helps you to find shortest path, to measure, some properties in your network if that's what you want. So the first example is asking us to create a graph with 5 nodes. So first step, we create the graph, right? An empty one. So we use the network X, we create the graph, then we create the nodes, which are the users. This can be cities or people. So here we're creating 5, right? A, B, C, D. You can add names if you want. And then the links or the edges, right? So that's how we connect them. You need to provide the pair. So we know that A and B are connected, A and C, B and D, C and D, and D and E, right? We have these links or these connections. So once we have defined the nodes and the edges, then we can just visualize the network graph. And this is how it looks. It shows how they are connected, right? So this is our first network graph. It's undirected. There is no like a direction in the connections. Now in the second one, in the second example, this is a directed graph and with weighted edges. That means that there is a cause or some information about the links. Okay, so this problem is about a delivery service tracks how often couriers travel between cities. The number of trips between the two cities is represented by weighted edges in a directed graph. So when we talk about directed graph, that means that there is an origin and a destination. So you will have arrows in our links. Okay, so let's create a directed graph representing the trips between 4 cities: New York, Boston, Chicago, and San Francisco. So first step, we create the graph. Please notice that now we have DI, because in the previous example, we will use graph. This is DI because it's a directed graph. So it means that the order matters when you define the pairs. Okay, so here then we start defining the origin, destination, and we also are providing the weight. Here is the trip frequency, right? But again, in other problems, this can be the cost or the distance. It depends, of course, of what you're trying to do. So we have all the connections here or the links. And then we can just visualize it. And now please notice that in the network, you can see the which is the origin and which is the destination, right? Because this is a directed network. Example number 3. In example number 3, and let me ask you this question. Let me just change the zoom here real quick. Maybe like this. Okay, there you go. I want you to please pause the video and try to find the shortest path between node A and node E. So these are distances or costs. What you see, the number that you see in the links, in the connections, that's a cost or a distance. So you want to minimize that distance or that cost of going from node A to node E. So please pause the video, 30 seconds, try to write down your solution, and now we will check it. All right. So yeah, you can do it. This one you can do it manually because it's a small network, right? But in general, if you have, let's say, thousands of nodes, that will be impossible. Okay, so in this one, there are some algorithms, the shortest path algorithm here, and you provide which is the source, which is the target, and of course which metric you're going to use, the weight here, or the cost of the distance. So it's finding that the best solution here is going from A to C, then to B, then to D, and then to E. So here we have the path, this one, A to C, then to B, D, E. How do I know that that's the shortest one? Just sum the values here. Find the total distance or the total weights. It's 2 plus 1 plus 5 plus 2 is equal to 10. So you won't find a better path if you want to go from A to E for this specific network. I'm sure that you try different paths here, but no, you won't find one. This is the shortest path, right? Because the one that minimizes the total distance. Okay, let's check our last example in the video. So in this one, a social media company wants to find the most influential users in a network based on the number of connections. So there are different metrics for this. Degree centrality is one of them. Create a social network with 10 users and identify the most connected users. So here we have the information of the 10 users, Alice, Bob, Charlie, the 10 persons here. We know the connections. It's given here, how they are connected. This is how it looks. This is how it looks. So just by looking at the graph, because it's a small graph, you can kind of spot and get an idea on which users are important, influential. So for example, I'm pretty sure that you will see that this one, if it's like kind of like right in the middle and it's heavily connected compared to, for example, Frank. Frank has only 2 connections. Same thing with Alice, David. They are, like in the corners with only 2 connections, while Evie and Charlie, they have 4, right? So for sure, when we measure the importance, we will find that Charlie and Eve are the most important or most influential, let's say, individuals in this specific network. So we're going to use 2 metrics here. The degree centrality, this one is simple, it's just it measures the number of direct connections. So this metric is estimated based on how many connections they have. That one is intuitive. This one is more interesting. The betweenness centrality. So the betweenness centrality is going to measure how often a node or a person in this case act as a bridge or is part of the shortest path between other nodes in a network. So like if you want to connect like two people in two persons in that network, so how often you will find that individual uh, in the path, right? In the shortest path. So that's how the betweenness centrality is measured. All right, so we can find them. There are, there's some methods here in the network X library to measure degree centrality and also to measure the betweenness centrality. So let's see what we get. For the betweenness centrality, we get that the highest it's if, right? If it's having like 0.35 is the highest one. Please note that Frank is 0. That means that Frank is not. When we check the like two nodes here, 2 individuals, and we find the shortest path between them, Frank is not there. Even, for example, if you want to find the shortest path between Charlie and Hank, they are close to each other, so there is a direct path, right? So you don't need to go through Frank, right? Now, but for example, if you want to if you want to connect Alice and Grace, uh, if you check the shortest path, there are 2 options. You can go through Bob and David, right, and then Grace, or you can go through Charlie and Evie and then to Grace, right? So Evie is right here, like in the shortest path, which here there are multiple between Alice and Grace. Evie is always right in the middle. So that's why there's her score, it's bigger. It means that she is found in most of the shortest path when you want to connect the different individuals in that network. All right, in the case of the degree centrality, there is a tie between Charlie and Evie because both are 0.44. That's because both of them they have the same number of connections, 1, 2, 3, 4, 1, 2, 3, 4, right? So then the most influential person in this network it's Evie. This is important if you wanna like spread something, news, or for advertising. Of course, it's useful to identify these users, right? Because of their importance. All right, I'm gonna stop the video for now. I'll see you in the next lecture.